Unit 6, okay, part A, steady state heat transfer. Okay, so as you know, we are having from the heat transfer conduction, convection and radiation. You know about conduction. Suppose if you take a wall from outer side to inner side, the heat will be transferred within the body. Okay, that is the conduction. If you take a convection, the heat will be transferred from that body, that wall to the inside of the room. Suppose in a winter season, from the sun, the heat will be distributed from the hot wall to the inside room. Between you have some medium, that is the air. Okay, that is the free convection. Suppose if you are using the fan or blower, that will be the forced convection. Similarly, you are having the radiation, that is from the directly from sunlight. We get the radiation. So in this we are discussed about the conduction and convection. Okay, let us take one wall close. Okay, in this, as you know, we are having different nodes: node 1, node 2, node 3, node 4 and node 5. We are having 1, 2, 3, 4 elements, each one having the thermal conductivity K1, K2, K3 and K4. And similarly, each one having temperatures T1, T2, T3, T4 and T5. We are having 5 nodes, 5 temperatures. Okay, if you observe this, from this starting, from compared to every element, the temperature will be dropped. As you know, initially the temperature will be more, at the end it will be decreased, because it is transferred from that point to this point. Okay, so initially due to the convection, we are having some medium. So due to the convection, there is the H, heat transfer coefficient, with some temperature T infinity, that is the temperature of the fluid, and H is the heat transfer coefficient. Okay, from that the heat will be transferred to this body. Here the conduction starts. Okay, this is a convection and here the conduction starts. Okay, and that this is the different lengths for different elements L1, L2, L3, L4. Okay, this is the T0, this is the outer temperature or inside temperature. So suppose if we apply the insulation here, as you know, here the temperature will be 0. That means there is no heat transfer, there is no temperature. That's why here this is a final T0 is equal to T5. So here it should be 90 angle. Okay, so here, as you know, in the last classes, bar, stress and beam, we are applying the boundary conditions, where you are consider the fixed supports as a fixed supports for the boundary condition. Here the insulation surface have to consider as a boundary condition. Suppose if you apply the insulation here, this will be fixed. That means that particular row will be cancelled, particular row and column will be cancelled. Like that in the other case, where we are using the KQ is equal to F, but here KT is equal to R. It should be correct, yeah? Okay. So KQ is equal to F where, but here KT is equal to R. Here K is equal to thermal conductivity K1, but we have to add all the K1, K2, K3, K4, you will get the capital K, and T is the temperature, okay, temperature vector, and R is the global heat load vector. R is the global heat load vector. So from this you find out that KT is equal to R. As you know here, see here. See, okay, here K1 is equal to K1 by L1, 1 minus 1 minus 1, 1. These all are the, to find out the capital K. Okay, here K1 by L1, 1 minus 1 minus 1, 1. This is similar to the earlier for bar element cases, where A1, E1 by L1, A1, E1, L1. But here in the place of A1, E1, we are having K1. Okay, K1. So K1 by L1, 1 minus 1 minus 1, 1. Similarly, K2 by L2, same. Similarly, K3, K. We are having 4 elements, 4, K1, K2, K3, 4s. Clear? Okay. And now after that, find out the individual values. We have to add all those values here. As you know, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 1, 2, 2, 3, 3, 4, 4, 5. Similar to 1, 2, 2, 3, 3, 4, 4, 5. Like that, you have to add all this. You know how to add. We already discussed in the last class about this. Okay. After then, you have to consider the matrix K is equal to R. Here, this is the all about K. This is the T, and this is the R. Okay. So if you observe this here, R is equal to R1, R2, R3, R4. But where R is equal to Q1 L1 by 2 1 1. Similarly, RT is equal to Q2 L2 by 2 1 1. This is considered only if Q is given. If Q is not given, that means Q1 Q2 is not given, where R1 R2 are zeros. So you can directly take the R1 R2 values as zeros. So if you given, you have to consider the formula as like this to find out the R1 and R2. After then R1 R2 you have to add R1 R2 and you have to find like this and you have to substitute here. Then you find the K is equal to R. But I already discussed earlier, this is K 1 5 2 5 3 5 and K 5, these values will be here. We are assumed as this is the insulation surface. That's why 5 1 5 2 5 3. This T5 entire this row and column and this value also will be cancelled. Okay. As you know, for the boundary condition, we are having two approaches. One is the elimination approach, and another one is the penalty approach. For the elimination approach, as you know, formula see same, but the small changes are here plus h and here h t alpha. That means h t infinitive. This is the only change. This is similar to earlier case, but here we have to add h and ht. Why we have to add h? As you know, where K are the different conductivities, thermal conductivity. We observe this HT alpha, where R1 is the, I'll discuss R is the global heat load vector, heat. Similarly, this is also HT also, this is the, as you know, we have a formula Q is equal to H A delta T, where Q by A is equal to H delta T. That is equal to H into, where T we can write as a T like that, T infinitive. Where Q by is the Q per area, or simply you can write Q per area or QA. So in place of Q by A, we are having the H, this one, H T infinitive, because this is also a heat load and this is also a heat load. That's why we have to add. Why we have to only for this one? Because here at the starting point only, from the convection to you will get the conduction. Here the due to convection the heat will be transferred to the starting point. From this point it will be distributed to remaining point. That's why you have to add what, but node 1 only, at starting point only you have to add heat. That's why H, that is the heat in terms of H, that means heat per area, that is the HT infinitive here. Similarly you have to add here H also. Okay, this is like this, it will model like this. And here we cancel the 5 5 to 5 3. That's why into that T5. That's why you have to subtract the value from this matrix. It will be positive. If it goes that side, it will be negative. That's why R1 plus H. Sorry, already we have discussed. Minus K51 T0. This is the last temperature is T5 or T0. Both are equal. This is the end temperature. This is the outer temperature or ending outer surface temperature. TO is T5 equal. That's why you can take here either T5 or T0. That's why 5-1 T0, 5-2 T0, 5-3 T0, 5-4 T5. Like that, we have to subtract all the values from this R1, R2, R3, R vector. Like that. This is the elimination approach. This is also now come to the penalty approach. In this penalty approach, okay, this is similar to this one, but as you know, we are discussing the for bar and beam and truss elements. Penalty approach, you have to take the C, that is the maximum Kij into 10 power 4. That is the maximum C, where C is equal to, you know about C. What is C? C is equal to maximum Kij into 10 power C here. This is the C. C. The formula for C is equal to maximum Kij into 10 power 4. Okay, that's why you have to consider C. That is a C. You have to add at the where it's a boundary condition we are taken. So here where the last step is, where you are taking the boundary condition, that place you have to add C. Similarly, you have to add the corresponding column. So K4 for R4. Here C, here CT naught. Similar to this one, we add H, here adding HT naught. Here C, here CT naught. This is same. So this value is not here. So that is the only difference between these two. So all this table same, this is also same, but in place of here you have to add C. Here C. This is same, but you don't need to add here. The difference is here we are having these values, here we are having extra C values. Here no C, here this no, this 5 and T naught values. Okay, like that you have to apply the elimination approach and penalty approach. Okay. Problem on the earlier concept. A composite wall consists of 3 materials as shown in figure. The outer temperature is T naught 20 degrees centigrade. Here is given the outer temperature 20 degree centigrade. Okay, 20 degree centigrade. Convection heat transfer coefficient takes place on the inner surface of the wall with T naught 800 degrees centigrade. See here, this is the convective temperature. And H is equal to 25 watt per meter square degree centigrade. Here is given H and T naught. Determine the temperature distribution in the wall. Okay, this is the question. Okay, so from the question is given the, and also given, see from this question is given K1, K2, K3. Here K1, K2, K3 and H and T naught is given in the question itself, and T naught 20 degrees centigrade in the problem. Okay, this let's take this is the L1, L2, L3. L1, L2, L3. We are having 1, 2, 3, 4. 4 nodes, 3 elements. Element 1, element 2, element 3. So K1, K2, K3. So you have to find out the individual values. K1, K2, K3. You have the formula in this with earlier discussion. This is the formula. So you have to use the same formula in this. K1 by L1, 1 minus 1 minus 1, 1. So you know K1, L1. You have to substitute here. You will find the value like this. Similarly, K2. Similarly, K3. But 1, this is okay. 1, 2, 2, 3, 3, 4. Like that, we have to take 1, 2, 3, 4, 1, 2, 3, 4. Okay, initially you have to give the naming as 1, 2, 3, 4. Okay, and KT is equal to R. See in this form. Let us first we are following the penalty approach method. So the based on this formula, so KT is equal to R. So here given the H value, and here HT naught value, and here CT naught value, and here C value. Similar to this formula, we are solving the first case. That is the, this is the C. This is the H. Is given H value as 25. This is the similar value. This is the K11, K12, K13, K14. So as you know how to add all these values. And similarly, here adding the plus C value. That is the C value is the maximum K is into 10 power 4. See here, the C value maximum K is into 10 power 4. This is C value. So that C value is added here. And similarly here, this value. See, as you know, here is not given the R1, R2, R3 values. So here we are given the, we are directly taken the R values as 0. We forget one point that if we given here R1, R2, R3, R4 as, you have to take zeros. If we given Q, we have to find the R value as Q1 L1 by 2 1 1. Similarly Q2. But if you not given Q values, you can take directly R as 0 0 0 values. So here also we are taken R1, R2, R3, R4 as zeros, and plus this is the HT naught. This is T naught value how much? 800. Similarly here also this is the plus C. Here plus C into T naught. This is the C value into T naught value is how much? Here T naught value, this is the 20 degree centigrade. Okay, here mentioned 20 degree centigrade. Okay, like that you are adding all the values. As you know how to do these calculations. Here get the formula as 3 by 3. So you can solve the equations by using calculator also. So simplify and you can get the values finally get like this: T1, T2, T3. So here you can find one this. See here, this is we add this one, you get 91 into T1 minus this into T2 plus 0 into T3. Okay, is equal to this value. The under value is equal to 20 into 10 cube. Similarly, second one minus 66 point T1 and this value into T2, this into T3 is equal to 0. But we observe the third one here 1, 2, 3, 4. Here earlier the T4 value is 0, but here the fourth we are having some value, that's why. So to get the equation by in 3 by 3, here T1 into 0, 200 T2, this value into T3, here we are having T4, but I want in 3 by 3, that's why this value will be go to that side, that's why 333 into T4, but you know T4 value that is 20 degree centigrade, that's why. So this value into T4 you get the some value that is equal to, now you are having the equation in 3 by 3 matrix. Now you can easily solve this equation, that's then you get the T1 T2 T3 values. Okay, this is the first case penalty. Similarly you can solve the problem in elimination approach. Yes, here this is the elimination approach formula. Okay, here we have to add H, here also HTR, and similarly phi 1 T 0 phi 2, where you are doing formula like this. So this is the similar matrix as above, T1 T2 T3 T4, we have to cancel these values. Similarly here R1 R2 R3 zeros, but here H, here H T 0. So here that's the fourth one, 4 1 T 0, 4 2 T 0, 4 3 T 0, 4 4 T 0, similar to the earlier problem, so formula. So here we cancel this one, that's why you have to take into that side. Now get the formula like that. So as you know here H into T 0 value, this is this value 0, 4 2 into 0 0, K 4 3 T 0, K 4 3, this value into T 0 value how much, 20. You get that. Here also equation looks like 1 2 3 3 by 3 equation, so you can solve easily using the calculator. You get the values like this. Okay, thank you. Now the second problem, heat is entering into a large plate at the rate of Q0, that is the minus 300 watt per meter square. This is a heat flux, that is heat per area is given here as shown in the figure. The plate is 25 mm thick, is the thickness is the 25 mm. The outside surface of the plate is maintained at a temperature of 10 degrees centigrade. The outside temperature is given as a 10 degrees centigrade. Using two finite elements is given, said that two finite, means you have to give it into two nodes, two elements. Okay, solve for the vector of nodal temperatures. So you have to find out the temperatures at different nodes and elements. Thermal conductivity is given as K 1 watt per meter degree centigrade. Okay, from this problem, so the given element, let us take the front view. So this is the Q0 is given and T0 is given. So as you know, element 1 2 3, you have 3 nodes and 2 elements, but 25 mm thickness. So where K1 Kd is equal, that is given as 1 watt per meter degree centigrade, but L1 L2 is the half of that entire length. So take L1 L2 is the 12.5 mm, so convert into meters. And similarly find out you have to find out the K1 Kd. We know the formula same, similar to this one. This is the 1 minus 1 minus 1 1, similar to the earlier formula. So you know K1 and L1 values, K1 L1, substitute here, you get the K1 and simplify like this. Similarly K2 values, you finally get the K value. As you know how to add, this is the 1 2, this is the 2 3, you know how to add 1 2 3. So observe 1 by 1. See here, this is the 2 by 2. So here 2 by 2 is here and 2 by 2 is here. So 80 plus 80, you know, that is the 160. You know how to add, I already told you in the last class. That's why you can easily add this one. Okay. After then, we have to use the KT is equal to R, similar to KQ is equal to F. So here K, then the T, then R. Okay, this is the K matrix. K 3 1 3 2 3 3. This is the and T 1 T 2 T 3 and R, similar to the earlier formula, R1 R2 R3 plus H T 0 and 3 1 T 0 3 2 3 1 3 2 3 3 T 0 3 2 3 3. Similar to that. So you know you have to find out here is not given Q value, so you can directly take in the R as a R values as a zeros. And here you observe this problem, I will tell you this is the HT0, but is not given H, is not given H value, but is given Q. As you know, HT0 is equal to what? Q. So in place of this HT infinitive, we can directly take the Q0 value. That's why is given Q0 in the problem, that is minus 300 watt per meter square. So in place of HT0, you have to take that value. That's why minus 300. Minus 31, K31 into 0. So 0 into how much T0 value is here? T0 value is given 10. This is 10 value. Okay. Similarly, K32 into T0. So that's the 8 minus 80 into that value. Similarly, K33 into T0, that is the minus 80 into 10 value. Like that you have to find out. Now take the remaining values, 80 minus 80, 80, 160. These two are cancelled, that means these two are go to that side. So T1, T2. So in this, so minus 300 and minus 80 into 10 minus of 80, so minus and minus plus 800. So finally you get the these values. You observe this in this here T3 here we are taking 0 because this is the outer surface, or we are taking as a consider as a insulation surface. There is no temperature in the at the end, that's why we are taking that 3 by 3 is cancelled. Okay, so this is the final, this is the 2 by 2 equation. As you know, you can solve very easily by using this, you can solve this problem. Okay, you can find out the T1 and T2. Okay, thank you. Okay, start. So this problem is similar to the earlier case, but if you observe this problem, in the earlier case is given the H in from inner side to outer side, from this side to that side. But here also is given from this side to that side, but here is given reverse. That is, this is the starting and this is the ending. That means this is the inner, this is the outer surface, this is the starting surface. That's why we have to take H, where here it's taken at a starting point. Here H, starting point, that is the here, that means here we taken at starting. But if you observe the problem, is given H in the at the end, so you have to take H at R4. Similarly per K14 also. Okay, that's the only difference. The remaining all is same. You have to find K1, K2, K3. You know, is given K1, L1, K2, L2 all. So you have to substitute all, and you have to combine the matrix. You have to use the equation. You have to find all the values. And you can get the 3 by 3 matrix. You can solve the equation very easily. Okay, thank you. In this, the problem is same, but the one difference is here is given the Q value. You observe this problem, K is given, and that value, heat rate, all are same, but determine the heat rate same. It is given Q in watt per meter cube. So I already told you, it is given anywhere Q, you have to find out the R2 and R1 separately, and you have to add R. You have to take the R values. So that's why you have to, here is given the Q value. So you have to find out the R1 R2 like this. See, as a formula Q1 Q2. Here Q1 and Q2 are same. So take Q1 L1 is given in the problem. This is the Q. L1 and L2 both are same. Q same for both values. So this L1, this is the L2, and this is the Q1 Q2 is same. This Q. That's why I am taken Q1 L1 by 2 formula. You get the value like this. Similarly, R2 is also same, but this is the 1 2, this is the 2 3. You have to find R values, R minus R2 like 1 2 3. So you will get the here see, this is the 2. So here 2 by 2, so 1 by 2, so here 1 by 2. We are having 2 1 by 2. So that's why you get the value as this is the 125 plus 125. This is the 250. So like that we find the second R value. Similar, the process is remaining same. K T is equal to R. So in that we just remaining process is same. But in here also we are having the H at the end, at the third node. So here also is similar to earlier case. Here also we have to consider the H at the end point, not starting point. Okay. The process is remaining same. Okay, thank you. Let us take the pin. Okay. So this is similar to earlier case, but very small difference is here Ki is equal to Kt plus Ht. Kt plus Ht. Because here you consider both conduction and convection. That is the final K. We will get the final K. Okay, here Kt is equal to K by Le 1 minus 1 minus 1. This is similar to the earlier case. Similar to the earlier case. Cl, if you want, see. K by L 1 minus 1 minus 1. This is similar to the earlier case. So that is this one. But the remaining is Ht is HLE by 3T 2112. This is one formula. Okay. HLE by 3T. This HLE by 3T you are already learned in the heat transfer subject. Okay. So if you see here, this is the perimeter of this pin. As you know, per rectangular pin, we have the rectangular length. Perimeter is 2 into L plus B. 2 here, 2 widths, this width and thickness also this one and this one. That's why we have formula 2 into W plus T. Suppose if it is a rectangle, as you know, this two widths, this is the width, this is the width, this is the some thickness. So 2W plus 2B. Similarly, here also 2 into W plus T. And similarly area, as you know, it is length into width. Similarly here, width into thickness. This is the area of the pin. I want P by AC formula. If you observe this formula, see, you can write this one as a 2W plus 2T. Compared to the width, the thickness is very small, so you can neglect the 2T. So that's why in place of P perimeter you can write as a 2W. So P by AC. So P means 2W and AC means the width. There is a circumference of the area. 2W by TW. WW cancel. You get the 2 by W. This is approximate to P by AC. That's from that. Actually, the basic formula is P by AC, HLE by 6, 2 and 1, 2. In place of P by AC, we can substitute 2 by T. 2 by T. Okay. 2 by T means, actually, P by AC means you can substitute 2 by T. So 2 and 6 cancel, you get the 3. This is the HLE by 3 into that T. So you can use any one formula. If you suppose if you given perimeter, you have to use this formula. If you given in terms of thickness and it's given thickness, you have to use this formula. Okay. Now you get the like that. If you add these two values, you get the Kij value. Okay. Similarly, R value. R is also similar to that one, but that formula in terms of R, in terms of Q1 L1 by 2 1 1. But here, we know the formula where Q is equal to what? HT naught. That's why you are substituting in place of Q. See here, Q. That means HT naught. LE by 2 1 1. Same. After that, similar process, you have to find out the Kij. That is the formula. After getting, you have to keep the enter one into like this. K1 1 1 2 1 3. Similar up to some L. Similar 2 1 2 2 3 1 3 2 up to L1 L2 L3. So now in this, here suppose T1 temperature is maintained at a node 1. This is T1 is equal to T0. As you know, the after the boundary condition, T1 is equal to 0. Both are equal. That's why you can neglect that value. And similarly, K2 2 2 3 12. So 3 2 3 3 and same T2 T3 T4. Here similar to that case, R1 2 3 4 minus 5 1 5 2 5 3. Here they are separated right as 2 1 3 1 up to some 4 1 5 1 L1 like that. T naught T naught. So this is a concept from fin. The formulas are similar. Okay. A metallic fin with thermal conductivity K. Okay, 360 watt per metric centigrade and 0.1 centimeter thick and 10 centimeter long. Extends from a plain wall whose temperature is 230 degrees centigrade. Determine the temperature distribution and amount of heat transferred from the fin to the air at 20 degrees centigrade with H is equal to 9 watt per meter degree centigrade. Take the width of the fin to be 1 meter. So this problem you have to solve by using the finite element. Okay, formulation. See, is given the figure here. T naught is T1 is equal to 235 degrees centigrade, and where this is the insulation at the end, the Q will be 0. And similarly is given H is equal to 9 watt per meter degree centigrade and T alpha T infinity 20 degrees centigrade. Here is given T is equal to 0.1 centimeters or 0.01 meters. W is equal to 1 meter. K is equal to 360 watt per meter degree centigrade. Similarly is given this is the 1 2 3 4 nodes. So L1 L2 L3. So L1 L2 L3 is equal to 3.33 centimeters is given. It's given as a 3 1/3 into 3 is equal to 10 centimeters. Each one is 3. So this is the, so that's why you are taking the 3.3 centimeters and convert into meters. This is the L1 L2 L3. This is a combination of all, but we want each one individual. That's why you are taken as like this. Similarly, K1 K2 K3 is equal to is given, that is 360 watt per meter. In the problem is mentioned this is the K. Okay, like that. Now come to here. Similar to the earlier case, you have to first find out the K. That is the KT. Okay, K1 by L1 1 minus 1 minus 1. The same formula. You get the K1. Similarly you get the K1. Okay, same formula. Substitute and find out. It's K2 and K3. This is equal to 1 2 2 3 and 3 4. Now we are add all that. This is similar to KT. This you get like this. Similarly, you have to find out the HT. I already discussed it here. The HT formula, HLE by 3T, or you can use this one. Here is given the thickness. So you are considering the HLE by 3T, 2, 1, 1, 2. You know H, LE, 3, T. Where H is equal how much? Where it is here 9 watt. See, 9 watt per meter square degree centigrade is given. That's why you are taking the H value. LE is here, and the thickness T, that is equal to 0.001 meters. Now you have to find like that. So finally you find the value like this. Once find out HT1, HT2, HT3, you have to find for individual nodes. So 3 nodes. After getting, you have to add all that 1, 2, 3, 4, 1, 2, 3, 4. You will find like that. You will get like this. This is the HT. But as per our discussion, you have to add KT plus HT to get the Kij. So come to here. You are adding this 2 matrices KT and HT, 1, 2, 3, 4, 1, 2, 3, 4, both. So you can add directly. You get the 1, 2, 3, 4. Okay, this is the final matrix. Now you have to use this one for the further process. Similarly, you have to find out the HT infinity to LE by T. This term is equal to Q. You know HT, all the values, substitute. Similarly, find for all 3 elements. So 1, 2, 3, 1, 2, 2, 3, 3, 4. You have to add all 1, 2, 3, 4. You get the R naught value. Now substitute in this equation. The equation is KT is equal to R. Okay, KTR is R value. Okay, that is after the elimination approach. You know, this is the K21, 31, 41. You have to cancel this value. Okay, similar to the earlier case, but this value, because here the starting we are having the providing the boundary condition. That's why we have cancelled that starting only. That's why from only T2, T3, T4. I will discuss it here. So T2, T3, T4. Here I am not considering the T1 and corresponding column rows. Here I am considering, here showing, but we are cancel these values. Okay, so that's why taking like this. Here KT is equal to R, where R values are, see, we are already 600, 1200, 1200, 600. But you have to here, you have to substitute these values, you know already. That's why there is a K21 into, I already told you, into T0. What is T0 here? The last temperature value. Here, this is the 20, here, see here, see, this is the 235. See here, see here. The T0 value, that's the starting temperature, outside temperature, 235 degree centigrade. The T0 into that corresponding K21. See here, K21 into that value. Similarly, K31 into that value, no need, 0. And K41 into that value. Like that, you have to take these values similar to the earlier. This is the elimination approach. Now you are the only 3 by 3. You can solve T2, T3, T4 by using that calculator. T2, T3, T4. This is the equation. But it's asking one more. There is amount of heat transport. That means how heat is lost. The formula HA delta T. HA delta T. That means T average minus T infinity. Okay, that. But here you have to find out for all individual elements. That is the sigma of combination of HA. So we are here. Come to here. That is H. T average minus T infinity into AS. And you found HA delta T. HA. Where AS is the surface area. Surface area. That's why 2 into the width into thickness or distance. It means 2 into where width is the how much? Where width is the in the problem mentioned. The problem mentioned 1 meter. Width is 1 meter and thickness. It's a distance. Distance means length. What is length here? Length is equal to 0.00 meters. That's why you have to consider the same for all individual loads. But here T minus T infinity is different for various numbers. Like that. This is the first case. 209 minus 20 initial. And AS. Similarly for second also, for second case. This is for 195 minus 20. And similarly, this is similar to the same. Similarly, the third one, 190 minus T. This is same. Like that, you have to add all this, you get this value. This is the final value. Okay, this is the final heat loss. Thank you.